So far in the limit comparison test, we've really dealt with things that compared to a p-series. Harmonic series is a p-series. This was a p-series. So that's a very common way of treating these. And so let's flip the paper over. Mine's a separate piece. And read. We can often compare sloppy algebraic series with a p-series, which is generally much neater, by using the limit comparison test. So I like the limit comparison test. We're going to, well, we have some fill in the blank here. We're going to compare the given series with a series of the same degree, fill in the blank with a series of known convergence or divergence, and circle the correct words in parentheses. This really cuts out a lot of the work, and we showed it here, but we realized too that if they have the same degree, then when we approach infinity, as we approach infinity, I'm going to get a finite positive number. So this is a very handy tool when I am comparing a couple series, and it could, if you strip away some of the unnecessaries, +5, and then the 3 coefficient, that is just stripped down, basically a harmonic series. And when you do that, you're going to get always a finite positive number. All right. This series compares with, okay, well, let's fill in the blank. What color do you want to use? Let's make this one red, he said as he picked up the red marker and then wrote on his thumb with it. All right. It's like I'm shouting at you. I feel like I'm shouting when I use red. Singing Les Mis songs. Okay, we're going to compare this with, okay, well, same degree. The degree is a 2 in the denominator, so make it a 2 in the denominator. This is a p-series. This p-series is, well, p equals 2. 2 is greater than 1, so it's going to converge. Therefore, this series will also converge. If you wanted to, you could switch to green, and you could do the limit as n approaches infinity of 1 over 4n squared minus 5n plus 5 over 1 over n squared, which would really just flip that thing over, and you're going to end up with 1/4, which is finite and positive. So if this converges, that converges, and I didn't show all that work, and I may have to on a free response question, but if I'm going fast, then that could be a p-series if you strip away all the unnecessariness. Let's move fast. Let's keep going. This compares with, whoa, now it gets tricky. Well, let's go ahead and start writing what we do know. It goes from 1 to infinity in this case, and it's 1 over, let's see. What's the degree of this? 1/2. Well, do I put the 5 in there? Nah, who cares about the square root of 5? This is what I care about. That's what I care about. This has the same degree as that. We've stripped away all the unnecessariness, which almost said converges. No, it doesn't. P-series, P is between 0 and 1, so it diverges. Therefore, the series they gave us also diverges. All right, here we go. Slide up slowly, then go fast. This compares with 1 to infinity of, well, let's do a fraction, and let's just, all the unnecessariness goes away. This minus n, the n to the 5th, the 14n, it's all gone, all gone, all gone. The 6, it's gone. None of that is important anymore. I am left with n squared over n to the 6th. Reduce that too. We are doing some reduction that in a truly multiplicative and division sense is illegal. But as we approach infinity and are comparing it to another series, all you need is the degree. That's all you need. Converge or diverge? It's p-series. P is 4. Converges, so this converges.